If you develop flexible packaging structures, or if you validate them, qualify them, or approve them, and you want to understand every lab test that stands between your design and a package that actually works in the real world, this video is for you. Flexible packaging is not just a film, it's a multi-layer system, each layer doing a specific job, and each one of those jobs can be measured. That is exactly what we do in the lab. I'm Mo. I have a PhD in polymer science and I work in product development for a flexible packaging manufacturer. Everything in this video comes from tests we run in actual packaging lab. Today I'm going to take you through every major category of flexible packaging lab testing: seal integrity, mechanical strength, barrier properties, optical and surface properties, thermal analysis, chemical resistance, and show you what each test measures, how it works, and why it exists. This is the most complete guide to flexible packaging lab testing you will find. Let us start from the foundation. Before we get into the tests themselves, I want to establish the framework because the tests are only as useful as your understanding of why they exist. Product development in flexible packaging follows 5 stages: incoming quality control of your raw materials, film structure validation, does the laminate you build meet a spec, seal process optimization, find the conditions that give you a reliable seal, barrier and functionality testing, does the structure actually protect the product, and finally, end use validation, does the finished package survive retort, freezing, distribution, and the consumer. Every test we will cover today maps to one of those 5 stages. And here is the critical point: none of them is optional. You cannot skip barrier testing because you are in a hurry. You cannot skip retort validation because the structure looks similar to something you have run before. The package that fails in the field is almost always the one where someone skipped a stage. There are 4 reasons testing is not negotiable. First, you must prove a performance with numbers. A specification without data is just a guess. Second, food, pharmaceutical, and medical packaging face regulatory requirement where the test report is your compliance proof. Third, product recall cost orders of magnitude more than the lab tests that would have prevented. First, your customer technical approval process require your document data. Without it, the structure never ship. I have organized all tests we are going to cover into 8 categories. Let me give you a quick overview before we go deep into each one. Seal integrity, the tests that confirm your package stays closed. Mechanical strength, how the film and laminate respond to force, tearing, and puncture. Barrier properties, oxygen and moisture transmission. Surface and optical tests, friction, gloss, haze, ink adhesion. Thermal analysis, DSC, melting temperature, retort resistance. Chemical resistance, how inks and coatings survive real-world contact. Dimensional and weight, thickness, grammage, moisture content, and microscopy. The test where you see what the naked eye cannot. What I want you to notice is that no category operates in isolation. A package that passes every field test but fails its barrier test is a failed package. A film with the correct OTR but the wrong COF will jam every machine it runs on. The categories interact, and understanding how they connect is what separates a good packaging professional from a great one. Before you can understand why you are running a test, you need to understand what you are testing. And in flexible packaging, you are almost never testing a single material. You are testing a multi-layer system where each layer has a complete different job. The outer layer, typically PET-oriented polypropylene or nylon, provides the mechanical backbone. It gives the package a stiffness, it carries the printed design, and it protects everything underneath from physical abrasion. The printing layer is where the ink, primers, and any overprint varnish live. This is the customer facing layer. It communicates the brand, but it also has to survive whether the package goes through retort, freezer, humidity, and handling. The adhesive layer. The adhesive layer bounds the structure film to everything below it. Two-component polyurethane system are the standard. The mix ratio, pot life, cure conditions, and substance compatibility all determine whether the bond holds. The barrier layer. The barrier layer is the protection layer. The reason the product inside stays fresh. EVOH, aluminum, foil, metallized films, ceramic coated films. Each has a different barrier mechanism and a different balance of properties. And the sealant layer, the innermost layer, is what actually closes the package. Under heat and pressure, it fuses to itself or to the opposing surface. Its melting temperature sets your sealing window. When you run a test on a laminate, you are measuring the combined performance of all these layers. And when something's fail, one of these layers is the root cause. The tests are your tools to find which one. Seal integrity. Seal integrity is the most fundamental category of tests in flexible packaging. If the seal fails, everything else is irrelevant. The best barrier film in the world is worthless if the package leaks. Seal uniformity. This is often the first test we run on a new structure. We seal a set of specimens at a defined temperature, pressure, and dwell time, then peel them and examine the pattern of the bound. We are looking for uniform adhesion across the full width and length of the seal. Any area that doesn't bound, a void, a channel, a tunneled section is a defect. Non-uniform seals are caused by worn sealing bars, inconsistent temperature profile, film thickness variation, or surface contamination. Leak test, also called hermeticity testing. This is your absolute go, no go. We place the sealed package in the dye solution and apply vacuum. Any opening in the seal draws dye into the package. Any color inside the seal zone is a failure. There is no partial pass. For medical packaging, this test is a regulatory requirement. For food packaging, it is your food safety baseline. Blistering test. When you seal a structure that contains moisture, trapped volatilities, or hydroscopic layers, you can get bubbles or raised area in their seal zone. The blistering test deliberately stresses the seal, usually through heat or pressure, to reveal latent defects before they appear in the field. Particularly important for retort pouches, where the steam cycle is aggressive. Face-to-face seal test. The sealant layer bonding to itself under controlled conditions, temperature, pressure, and dwell time. This is how we built the seal heat seal window, which we will cover in the next slide. Blocking test. This one catches people off guard. Blocking happens when film layers stick to each other in a wound roll or stack sheets, usually during storage in heat or humidity. The test applies a defined load and temperature to stack specimens, then measure the force to separate them. A film that blocks on the roll cannot unwind on the machine, and this is the production stoppage. Perforation check. Every easy tear feature on a package, tear notches, zip strips, perforated openings, must be verified for position, cleanliness, and function. A perforation that tears in the wrong direction or requires scissor to generate end user complaints as scale. Okay, this slide is the most important in the entire video of anyone involved in seal development. The heat seal strength curve, also called seal window curve, is the single most useful piece of data you can generate for a new structure. On the horizontal axis, sealing temperature. On the vertical axis, spill force, how much force it takes to separate the seal. The curve starts low, rises steeply, then goes to the plateau. The plateau is where the sealant is fully fused and the film itself becomes the limiting factor, not the seal. The red dashed line is your minimum specification, the lowest acceptable seal strength for your application. The region between the minimum spec temperature and the plateau is your sealing window. The width of the window determines your process robustness. The width of the sealing window matters as much as the seal strength itself. A window of 10 degrees Celsius means any temperature fluctuation on your production machine, and they always fluctuate, risk falling below spec. A window of 40 degrees means you can absorb seasonal variation, machine wear, and lot-to-lot film variability without a single out-of-spec seal. Now let us talk about peel test geometry, because you will see several methods referred in a specification. The 180 degree C. The 180 degree peel is the industrial standard for laminated structures. One substrate is folded straight back and pulled at 180 degrees. It is measured on a tensile tester, the Instron, and reported in Newton per 15 millimeters. The T-peel. The T-peel test is used when both substrates are flexible and not self-supporting. A foil-to-foil seal, a thin film-to-film bond. Both arms are peeled simultaneously at 180 degrees, forming a T shape. The 45-degree peel. The 45-degree peel simulates the angle at which a consumer opens a leading tray or peel tap pouch. It is especially relevant for easy peel application where the peel force must be high enough to survive distribution but low enough to open by hand. The hand peel is the fastest quality check in the lab. You peel the seal by hand and look for the failure mode. If the substrate tears rather than the seal separating, the seal is stronger than the film. That is what you want. If the seal peels cleanly at the interface, that is the seal failure. The hand peel is used every day in production QC because it takes 5 minutes. Let's go to mechanical strength test. Mechanical strength tests tell you how your film and laminate responds to force. And force comes from every direction in real packaging use. Machine pulling and stretching the film. Products pushing outward from inside. Consumers tearing, bending, and dropping. Distribution abuse over days and weeks. The first test, burst test. The burst test pressurized the sealed pouch with air or liquid until it ruptures. The burst pressure tells you the maximum the package can withstand, but more importantly, where it ruptures tells you which is the weak link. If it bursts through the film body, the seal is stronger than the film, which is typically the design goal. If the burst at the seal is the weak link, and you need to investigate. Curl testing. A film roll that curves when laid flat creates a registration problem during printing and lamination, and seal jams on every machine it runs through. Curve comes from internal stresses, usually residual tension from the lamination process or a thermal gradient in the oven. We measure it by cutting a defined sample and measuring the deflection from flat. Any structure outside the tolerance specification for the converting machine will cause production problem. The pinhole test, particularly the Gilbo flex test, is critical for barrier film. The Gilbo tester mimics the repeated flexing, twisting, and crushing that the film experiences during distribution. Filling lines, conveyors, transportation. Every flex cycle is an opportunity for a pinhole to form in the barrier layer. A single pinhole through an aluminum foil layer can destroy the OTR performance of an otherwise excellent structure. Tear force. This is both a product integrity test and consumer experience test. Easy open features, tear notches, laser scoring, microperforation must initiate, cleanly, and propagate in the intended direction. A package that requires scissors or one that tears in the direction that contaminates the product is a package failure regardless of its other properties. The rub abrasion test, also called the Sutherland rub test, measures how well the printed surface resists contact during distribution. 50 packages of a product rubbing against each other in a shipper carton over 1,000 kilometers of road. The ink must not transfer. Any visible ink on the rubbing surface after 50 cycles means the coating or ink adhesion is inadequate, and you have traceability and potentially food contact issue. Thickness uniformity. Measure at 10 or more positions across the web width. Thickness variation of even 2 or 3 microns in 25 micron sealant film cause inconsistent seal across the web. Barrier properties different from the left edge to the right edge of the roll, and dimensional problems during thermoforming. Barrier properties are the reason multilayer film exists. The whole point of building a complex laminated structure with an EVOH layer or an aluminum foil layer or a ceramic coated film is to control what passes through the package well. And the only way to know if your barrier is working is to measure it. Look at this table. OTR, oxygen transmission rate, in cubic centimeter per square meter per day, and WVTR, water vapor transmission rate, in grams per square meter per day. These are the two fundamental barrier specifications. For a snack food, chips, crackers, you need an OTR below 1 cubic centimeter. For coffee and roasted nuts, you need below 0.1. For meat in modified atmosphere packaging, below 0.05. For pharmaceutical, you can be down to 0.01 or lower. These are the orders of magnitude apart, and the structure you design must be calibrated to the exact product you are protecting. The OTR test is run on a Macon OX strand or equivalent instrument at 23 degrees Celsius and 0% relative humidity. WVTR is typically measured at 38 degrees and 90% relative humidity, tropical conditions, to get the worst case measurement for products that will be distributed in warm, humid climates. Fresh product in modified atmosphere packaging is most complex barrier case. The OTR must be matched to the respiration rate of the product, the amount of oxygen the produce consumes per square meter per day. If the OTR is too low, CO2 builds up inside the package and produces suffocates. If it's too high, the modified atmosphere packaging benefit is lost. The specification is a range, not just a maximum. Both directions can cause product failure. FTIR spectroscopy, infrared spectroscopy, is your forensic tool for barrier analysis. When an OTR result is unexpectedly high, when eliminate is eliminating, and you don't know which layer is the problem, when you need to confirm that the barrier coating is actually present and in the right quantity, FTIR gives you the chemical fingerprint of every layer in the structure. It identifies functional groups, confirms the material identity, and tracks chemical changes like adhesive cure or coating degradation. Let's go to the surface properties and optical tests. Surface and optical tests are the ones that determine whether your film can run on a machine and whether it looks the way the brand requires. A film with perfect barrier properties and perfect seal strength is useless if it jams the machine or looks hazy on the shelf. The coefficient of friction test measures how much force is needed to slide the film surface across itself or across a metal surface. Or on a vertical form fill seal machine, the film wraps over the forming tube, slides through the sealing jams, and advances through a series of guides. Every one of those contact points involve friction. The static COF is the peak force required to start the sled moving. The kinetic COF is the force during sliding. Both are important, but for different reasons. The static COF controls how machine starts a new film cycle. The kinetic COF controls the running speed and the smoothness of the film advances. Target range is between 0.1 to 0.3 for both film to film and film to metal. Too high, above 0.4, and the film drags, misregister, and jams. Too low, below 0.05, and you lose control of the film. It slips unpredictably through the machine, and here is the hidden problem. COF changes with temperature and humidity. A film that runs perfectly at 20 degrees Celsius in a climate-controlled plant may behave completely different in a hot, humid summer. In a controlled facility, we always test at the actual running condition. For the ink adhesion, a tape pull test, we apply standard adhesive tape to the printing surface with a defined pressure and pull it away sharply. Any ink on the tape means adhesion failure. This test is run on a fresh prints. Then again, after retort, after freezer cycling, after high humidity storage, because each of those conditions stresses the adhesive bond between ink and the substrate. Haze and transparency. For clear packaging, fresh milk produce baked goods, the consumer judges product freshness by what they can see through the film. Haze is measured as a percentage of the transmitted light that scatter more than 2.5 degree from the beam direction. A clear PE film should be below 5% haze. As haze increases, the film looks cloudy, old, and unappealing, even if the product inside is perfectly fresh. Glass is a reflection metric. Glass is a reflection metric. High glass films above 80 glass units at 60 degrees looks premium and crisp. Matte films below 10 glass unit give a sophisticated artisanal look. Inconsistent glass across the web surface is the most common indicator of uneven coating application or non-uniform corona treatment. Thermal analysis connects the molecular structure of your material to their processing behavior, and its flexible packaging. The most important thermal analysis tool is DSC, differential scanning calorimetry. Look at this curve. On the horizontal axis, we have temperature. On the vertical, we have heat flow. As you heat the sample, you see the characteristics events. First, the glass transition temperature, TG. This appears as a step change in the baseline, not a peak. Below TG, the polymer chains are frozen and the material is rigid and brittle. Above TG, the chains gain mobility and the material becomes rubbery and flexible. For packaging films, TG determines the low temperature brittleness limit of the structure. Second, cold crystallization, TC. For semi-crystalline polymers like PET or PLA, chains that didn't crystallize during processing can organize into crystals on heating above TG. This appears as an exothermic peak. Heat is released. It tells you about the thermal history of the sample and how crystallizable the polymer is. Third, melting temperature, TM. This is the most directly useful measurement for sealant films. The melting temperature of your PE sealant tells you the minimum temperature at which the sealant chains can fuse to form a bond. If your PE sealant melts at 120 degrees, you cannot form a reliable seal at 110. If you try, you get cold seal, weak, inconsistent, and prone to failure. The melting temperature of the sealant layer sets the bottom of your sealing window. DSC also measures the degree of crystallinity, the proportion of polymer that is organized into crystalline domain. More crystalline means better barrier performance because oxygen and moisture must fill a path through the disordered amorphous region. A highly crystalline PE sealant has a better barrier but requires a higher sealing temperature. A less crystal version seals more easily but leaks more. Beyond DSC, thermal analysis in flexible packaging includes ink thermal resistance testing, running printed specimens through a full retort cycle at 121 degree and inspecting for adhesion loss, color change, and cracking, and OPV cross-linking verification confirming that the overprint varnish has fully cured using MEK, ROP test, or FTIR spectroscopy. Chemical resistance and end-use simulation tests are where we ask the hardest question. Does this package structure actually survive everything it will encounter in real life? The most aggressive of this is retort sterilization simulation. Retort packaging, canned soup, ready meals, pet food in flexible pouches goes through a sterilization cycle of 121 degrees C, 15 psi for up to 90 minutes. We replicate this exactly in laboratory, autoclave, then immediately evaluate the structure. What do we look for post-retort? Is the ink still bounded? Has the laminate delaminated anywhere? Is there haze, blistering, or color change in the seal area? Is the peel strength still within specification? Every one of those failures is a product safety issue. Retort testing is not optional for the retort application. Ink chemical resistance testing uses food contact simulants defined by regulation. 3% acetic acid for acidic food, 10% ethanol for alcoholic product, refined olive oil for fatty food, distilled water. We immerse a specimen in these simulants for defined durations, then measure ink adhesion and gloss retention. The regulatory threshold for a food contact structure is zero visible transfer under the test condition. Residual solvent retention. Every solvent-based ink and every lamination adhesive introduces solvent into the structure. Those solvents should evaporate completely during the drying and the curing process, but some always remain trapped in tiny quantities. between the layers adsorb into the film. We measure this by GC headspace analysis, a technique sensitive to parts per billion. The food contact limit for the total residual solvent is typically 5 milligrams per square meter. Above that threshold, you have an odor problem at minimum and a food safety concern at maximum. For paper-based sustainable packaging structure, the COBB value is critical test. We place a column of water on the paper surface for exactly 60 seconds. Then weight the absorbed mass. A well-coated barrier paper should absorb less than 20 grams of water per square meter. An uncoated kraft paper can absorb 100 grams or more. If your sustainable paper packaging cannot resist moisture absorption, it loses dimensional stability, print adhesion, and barrier performance all simultaneously. Let's go to microscopy, dimensional tests, and specialty methods. Microscopy gives you access to information that no other test can provide. The actual physical structure of your film, visible at micron and submicron scale. Scanning electron microscopy is the most powerful diagnostic tool in packaging laboratory. When a laminate is determining, and you cannot determine from chemical tests or peel tests whether the failure is at adhesive substrate interface within the adhesive layer or at the barrier layer interface, the SEM shows you. We prepare the cross section by cryofracturing the sample in liquid nitrogen. The cold fracture gives you a clean break that doesn't deform the layer boundaries. Under the electron beam at 500 to 5,000 times magnification, you can count every layer, measure each one's thickness, and see the quality of every interface. A properly bounded laminate has a sharp, clean boundary between layers, and the lamination-prone structure shows microvoid contamination particles or a weak boundary layer that the bound never fully penetrated. Combined with EDX, energy dispersive X-ray spectroscopy. The SEM gives you elemental maps. You can confirm that the aluminum oxide barrier coating is present and at the correct thickness. You can identify the silicon-based contamination particle at the film interface. You can verify the presence of primer layer that is invisible to every other test. The digital microscopy is a faster, more accessible tool for routine surface inspection. It operates at up to 6,000 time magnification under visible light. No sample preparation required. We use it for seal quality inspection, pinhole imaging, ink adhesion failure documentation, and surface defect analysis. Anytime something looks wrong on the surface of the film and you need to understand it at a scale beyond a hand lens, the digital microscopy tool is the first one that you can use for testing that film. Barcode verification is the test that the people think of as a printing check, but it is actually a product traceability requirement. Every barcode on a package must achieve a minimum grade. Grade C for retail, grade A for medical and pharmaceutical. When scanned by reference grade verifier. A barcode that fails in the field means that the product cannot be packed, the product cannot be tracked through the supply chain. This is not a cosmetic problem, it is operational and regulatory problem. There are more tests that you can see in the slide, and if you have any question about those, you can comment in the comment section of this video. Let's go to the building a testing strategy, which tests for which structure. Now that you know all the tests, the practical question is which ones do I actually run? And the answer is it depends entirely on the end use. For a retort food pouch, the most demanding application in flexible packaging, you run everything: seal uniformity, leak test, burst, OTR, WVTR, retort resistance for both inks and the laminate structure, residual solvent retention, DSC for the sealant, and peel strengths at the multiple peel geometries. Every one of those is mandatory because a failure means contaminated food and a recall. For medical packaging, under ISO 11607, the test panel is different but equally demanding. The regulation requires documented peel force, burst pressure, and leak test data from a validated method and calibrated instruments. Stroli barrier validation is not a suggestion. It is the regulatory basis for putting a sterile product in the hands of a healthcare professional. For snack food or dry goods, the critical tests are OTR for barrier, seal uniformity, and leak for the package integrity. Peel strength to establish the seal window, CO for machinability, and haze or transparency for consumer shelf appeal. Fresh product in modified atmosphere packaging adds a different dimension. The OTR target is not just a maximum, it's a range. Too low and CO2 accumulates. Too high and the atmosphere equilibrates too quickly. You need to characterize the film's OTR and match it to the product respiration profile. This requires more testing, not less, because you are optimizing a dynamic system. The pro tip I want to carry out of this video: on the first production trial of any new structure, run the full test panel. You will never have a better opportunity to establish a complete baseline. Under qualification, after a raw material change, a new film supplier, a new ink system, a new adhesive grade, run the tests that are affected by that change, but document every test you waived and your rationale. If you cannot explain in writing why a test was waived, you should not have waived it. 7 things that I want you to take away from this video. 1. A multilayer film has 5 distinct rules, and each rule can be tested independently. Understanding the structure is the prerequisite for understanding the test. 2. Seal integrity is your first priority. A package that cannot stay sealed fails before it ever reaches the customer. The seal uniformity, leak test, and peel strength are your baseline of every time. 3. The heat seal window is your process robustness. A narrow window means a fragile production process. A wide window means you can absorb a machine variation, seasonal temperature changes, and lot-to-lot film differences without a single out-of-spec seal. 4. OTR and WVTR are not negotiable for any structure claiming to protect its contents from oxygen and moisture. A claim without a measure number is not a specification. 5. COF is not glamorous, but it is critical. The wrong friction value creates production problem that follow a structure for its entire commercial life. 6. DSC connects material chemistry to processing behavior. The melting temperature of your sealant tells you your sealing window. Crystallinity tells you your barrier. And lot-to-lot DSC comparison tells you if someone sent you the wrong resin. 7, and the last one, build your test panel around that the end use. Retort pouches and snack bags look similar on the outside, but require completely different test priorities. If you work with any of these tests in your lab Or if there is a specific test or failure mode you want me to cover in the dedicated video, drop it in the comments. I read everyone. Subscribe for a new video every week on polymer science and flexible packaging. I will see you in the next one.